Hello friends, I welcome you in lecture number 8 on functions. In this lecture we will discuss this example on functions and we will discuss conditions for invertibility of a function. So first we do this example. Let f be a function from R to R given by fx equal to x cube minus 2 and we are asked to find out inverse of this function f. So we can first check whether this function is one-to-one and onto, because we know that function is invertible if it is one-one and onto. So first we check for one-to-one. So for that we take two elements in the domain. Here domain is the set of real numbers. Let x, y belongs to R such that their images are equal, such that fx equal to fy, and if function is one-to-one, then this must implies that x and y are equal. Now fx is given by x cube minus 2, therefore fy will be equal to y cube minus 2. So therefore x cube equal to y cube, and x cube and y cube are equal if x equal to y. So therefore fx equal to fy implies x is equal to y. That means f is 1-to-1. Now we check for onto. For that we consider any element in the codomain and we will show that there exists some element in the domain whose image is that element. So we show that for each element in the codomain there exists its pre-image in the domain. So for that let y be in the codomain. Here domain and codomain are same set of real numbers. So we start by considering any element of the codomain. Let y be in the set of real numbers which is codomain of given function. Then if function is onto, then for some x in the domain, if f is onto, then y will be equal to fx for some x in the domain if function is onto. So first we assume that suppose y equal to fx for some x in the domain, and if this is true we will be able to find out value of x in the domain such that y equal to fx. Therefore y equal to fx is given by x cube minus 2, therefore x cube will be equal to y plus 2 and hence x will be equal to 1 by 3 power of y plus 2. So this x must be a real number. So that is obvious because y is a real number, y plus 2 is a real number, and y plus 2 raised to 1 by 3 is also a real number. So this is in the domain. This is a real number, and the element which we have selected from the codomain is arbitrary element. So we can say that for any element in the codomain there exists some x in the domain such that fx equal to y. Therefore f is onto. So now we can write that hence for any y in the codomain which is set of real numbers, for any y in the codomain there exists x which we have obtained as y plus 2 raised to 1 by 3 in the domain, such that if we find out value of function at this x, then that is going to be equal to y, such that fx equal to, now fx is given by x cube minus 2. Before that we put x equal to y plus 2 raised to 1 by 3. Fx is given by x cube minus 2. Therefore we have to take square of this not square, cube of this minus 2. Definition of given function is image of x is cube of x minus 2. Instead of x we have y plus 2 raised to 1 by 3, so we take cube of y plus 2 raised to 1 by 3 minus 2. So we are using the definition of given function. Y plus 2 raised to 1 by 3 into 3, that is y plus 2 and minus 2. So we can see that fx equal to y. So this shows that our function is onto. So because f is 1 to 1 and onto, so we can say that f is bijective. And if f is bijective, we can talk about its inverse. And f is a function from R to R. Therefore, f inverse is a function from R to R. And we can say that f inverse exists. Now to find out f inverse, we are using the definition of inverse. We know that if f is invertible and fx equal to y, then f inverse y will be equal to x. So we will find out value of x, and we have already obtained the value of x in proving that ontoness. So now we first find out roughly fx is equal to y. Therefore, actually we are interested in the definition of inverse, f inverse from R to R. So because f inverse is defined, f inverse is a function, that means for every y in the domain there must be some element in the codomain which is unique. So we assume that f inverse y equal to x, therefore fx equal to y, and we try to find out value of x. So whenever we want to find out inverse of given function, we will find out value of x from this formula of given function. We will simplify this formula so that we obtain x in terms of y, and x is nothing but f inverse y. Fx is equal to y. This implies x cube minus 2 equal to y, because fx is given as x cube minus 2. This implies x cube equal to y plus 2, and this implies x equal to y plus 2 raised to 1 by 3. And we know that if function f under function f, if y is the image of x, then under function f inverse, x is the image of y, that is f inverse of y equal to x. So here we replace f inverse y by x, and we obtain that f inverse y is given by f inverse y equal to y plus 2 raised to 1 by 3. So this is the way how we can decide the inverse of a function. So we just rewrite all these things systematically, but always remember, if function f is invertible, suppose f is a function from a to b which is 1 to 1 and onto, then f inverse will be a function from b to a, and if fx equal to y, then x will be equal to f inverse y. So here image of x under f is y, here image of y under f inverse is x. So we will always be interested in the value of x, that we will denote by f inverse y, and that we will obtain by simplifying this relation. We will find out x in terms of y after simplifying this formula of given function. So here we have obtained f inverse y equal to y plus 2 raised to 1 by 3, and that we write systematically f inverse from R to R exists. Now we take any element in the domain, let y belongs to R. Now this is domain of f inverse, so we consider y in the domain of f inverse, and let f inverse y equal to x. So we are interested in the formula of x, This gives me y equal to fx by the definition of inverse. We know that if fx equal to y, then x equal to f inverse y. So therefore y equal to x cube minus 2. We are interested in the value of x. Therefore x cube equal to y plus 2, and therefore x equal to y plus 2 raised to 1 by 3, and x is nothing but f inverse y. Hence we obtain the formula for f inverse. Image of y under f inverse is y plus 2 raised to 1 by 3. So this is the formula of inverse function. If we wish, we can change this variable y by x also. F inverse x is given by x plus 2 raised to 1 by 3. X belongs to R. F inverse is a function from R to R. So in this way we can easily find out the inverse of a function. We just remember that we will find out value of x after simplifying this fx equal to y, and here we obtain that x is equal to y plus 2 raised to 1 by 3, and x is f inverse y. So this is the inverse function of given function, which is fx equal to x cube minus 2. So in this way we can easily find out inverse of a given function, provided given function is 1 to 1 and on to. Now from this example we observe certain things. Here fx is x cube minus 2, and f inverse we have obtained. F inverse of x is the function f inverse x is x plus 2 raised to 1 by 3. Both are from R to R. F inverse x is x plus 2 raised to 1 by 3, and both are functions from R to R. Now suppose we find out composition of f and f inverse. Suppose I find out f composite f inverse. Because domain and codomain of both the functions are same, f composite f inverse as well as f inverse composite f will exist. F composite f inverse at point x is given by f of f inverse x by the definition of composition. So this is going to be f of x plus 2 raised to 1 by 3. Value of function at x plus 2 raised to 1 by 3. Value of f. Now fx is given by x cube minus 2, and instead of x we have x plus 2 raised to 1 by 3. So we have to take cube of this minus 2, because we are using this formula. If we have x, then image of x is cube of x minus 2. Instead of x we have x plus 2 raised to 1 by 3. So its image is cube of x plus 2 raised to 1 by 3 minus 2. And if we take cube of x plus 2 raised to 1 by 3, we will obtain x plus 2 and minus 2. So that is x. So we obtain that composition of f and f inverse is giving x back, or image of x under f composite f inverse is x, and we have discussed that the function which sends element to itself is known as identity function, that we can denote by I suffix r at point x. So what we have observed that for this function, composition of f with f inverse is identity function. Similarly, if we consider f inverse composite f, then that is also going to be identity function. Now instead of this, suppose we consider f inverse composite f, then here I have f inverse, here I write fx. Now instead of fx, fx, now fx is x cube minus 2, so here I write x cube minus 2. Here I have f inverse. Now I am finding composition of f inverse and f. f inverse composite f x equal to f inverse of fx. Fx is x cube minus 2 and f inverse is x plus 2 raised to 1 by 3. So here we have x cube minus 2 plus 2 raised to 1 by 3. Now we are using the definition of f inverse. Image of x under f inverse is x plus 2 raised to 1 by 3. Instead of x we have x cube minus 2. So here we put x cube minus 2 and plus 2 raised to 1 by 3. So this 2 will cancel out and we have x cube raised to 1 by 3, that is again x. So that is also identity function at point x. So another thing we observe is composition of f inverse and f is also identity function. So in this example we have seen these two compositions. Composition of f and f inverse is identity function. Similarly, f inverse composite f is also an identity function. So now this is not the case for this function only. If we have an invertible function f, any function f which is invertible from any set to any set, then if we take composition of f with its inverse, then we will always obtain identity function. So this is a cross check also. Suppose you have obtained inverse of your function, and if you want to check whether it is correct or not, you can simply find out composition of f and f inverse, and if that composition is identity function on a given set, then your inverse function you have obtained is correct. So remember this. This I have written as a theorem. If f is a function from a to b which is invertible, then f inverse composite f equal to identity function on set A. Here domain of f inverse f is A, therefore here I have written identity function on A. And f composite f inverse will be equal to identity function on B. If f is a function from A to B, then f inverse will be a function from B to A, and domain of f composite f inverse will be equal to domain of f inverse. So here we have written identity function on set B. So if function is invertible, then composition of f and f inverse are always identity functions. Some authors use this capital I notation for identity function on a set A. That is also valid. So instead of small I suffix b, we can use capital I suffix b, and here also we can use capital I suffix a. Both are the valid notations for identity functions. So if f is invertible, f composite f inverse is identity function, as well as f inverse composite f is identity function. Now another condition for invertibility is that if two functions are given, suppose f is a function from a to b and g is a function from b to a, then this function g will be inverse of this function f if and only if their compositions are identity functions. Suppose you are given two functions and they ask you to check whether those two functions are inverses of each other or not, then you have to check their compositions. If their compositions are identity functions, then those two functions are inverses of each other. Here f is a function from a to b, g is another function from b to a, then g is inverse of f if and only if g composite f equal to identity function on set A, which is domain of g of f, and f composite g equal to identity function on set B, which is the domain of set G. So remember these conditions for invertible functions. They can ask you, they can give you two functions and they can ask you to check whether given functions are inverses of each other or not. If you want to check that whether given function is invertible or not, then for that condition is that function must be 1 1 and onto. If given function is 1 1 and onto, then that function is invertible. We can define its inverse. But if we are given two functions and if they ask you to check whether those two functions are inverses of each other, then we will find out their compositions. We will find out compositions of f and g and f, and if these two compositions are identity functions, then we can say that function g is inverse of f or function f is inverse of g. So remember this condition for invertible functions. We consider one example of this type. We are given two functions, fx equal to x cube and gx equal to x raised to 1 by 3 for x belongs to R, and we have to show that these two functions are inverses of one another. And here x is given in the set of real numbers for both the functions. So we can write that both the functions are having same domain and codomain. We consider domain as set of real numbers, codomain as also set of real numbers. Therefore, compositions GOF and FOG will also be a functions from R to R. So now first we check what is composition GOF. So for that we take any element in the domain of GOF. For x belongs to R, we check what we obtain for this GOF, value of GOF at any point x. This is equal to, by the definition of composition, it is g of fx. Fx is given as x cube, so here we replace fx by x cube. Okay, here we can mention that because fx is given as x cube. Gx is x raised to 1 by 3. Image of x is x raised to 1 by 3. So here we first mention in the bracket that g of x is x raised to 3. Therefore g of x cube is x cube raised to, gx is not x raised to 3, it is x raised to 1 by 3. Gx is x raised to 1 by 3, so therefore g of x cube is x cube raised to 1 by 3, and this is going to be x. And domain of GOF is set of real numbers, so here we can say that this is identity function, value of identity function at any point x in set of real numbers. Okay, this is the definition of identity function. Ix equal to x, x belongs to R, therefore we consider here in the suffix we write R. So we can see that for any x belongs to R, these two functions are equal. What we have shown that therefore value of this function GOF at any point x is equal to value of identity function at any point x. Here we write that this is true for any x in the set of real numbers. Therefore these two functions are equal. GOF is equal to identity function on the set of real numbers. Now we check another part. We find out FOG and we see whether we obtain identity function or not. So now we consider again for any x in the domain of FOG, we try to find out FOG at this point x. This is going to be f of gx by the definition of composition. And what is gx? Gx is given to be gx equal to x to the power 1 by 3. So that we substitute here gx equal to x raised to 1 by 3. Now we require formula of fx. Fx is x raised to 3, and instead of x here we have x raised to 1 by 3. Therefore we consider third power of x raised to 1 by 3. and that is equal to x, and this is also value of identity function at point x. Okay, here we can mention that because IRX equal to x for all x. So here also we obtain identity function, therefore value of fog at any point x is equal to value of identity function at any point x, and x is any real number for any x belongs to R. Therefore fog equal to identity function on the set of real numbers. So both the conditions are satisfied. GOF is identity function, fog is also identity function. So we can combine both the conditions. Thus composition of G and F is identity function, as well as fog is also identity function on the set of real numbers. Therefore F and G are inverses of one another, or inverses of each other, inverses of one another. So in this way, if we are given two functions, one function f from a to b and another function g from b to a, then f equal to g inverse if and only if GOF equal to identity function on A, here domain of F we will consider, and FOG equal to identity function on the set B, here domain of B. So this is the condition for invertibility, to check whether two functions are inverses of each other or not. And if you are given a function f, and if they ask you to check whether that function is invertible or not, then you have to show that that function is 1 1 and onto. So function has an inverse if it is bijective or 1 1 and onto, and two functions are inverses of each other if their compositions are identity functions. So in this lecture we have discussed conditions for invertible functions. I hope you like this lecture. Thank you very much.